Hi learners, students, good morning to you all. So myself Professor S. Kripanidhi giving a series of talks from the Department of Biotechnology, Vignan's Foundation for Science, Technology and Research, Andhra Pradesh, India, on and immunoinformatics. Hitherto we covered overview of the immune system. In the second unit was on immunoglobulins. And the third unit is on the techniques involved in immunology. Okay, so in this, the topic is on Elisa and RNA. In this technique, antigen-antibody interaction, that is the title for unit 3, wherein we are seeing the Elisa and radioimmunoassay. The first topic was antigen-antibody precipitation and agglutination. Okay, now in this, Elisa is a noble laureate topic. So this RIA, so Rosalind, as a woman scientist, she got the Nobel Prize for identifying the protocol for radioimmunoassay. Okay, so this is ELISA RIA. So this is ELISA is a modified version, simplified version further compared to the RIA. So through this ELISA, at any remote corner, we can do the, what is that called, the diagnostics. Particularly, we are doing now the diagnostics of our coronavirus. Okay, so wherein IgM, IgG, our people are evaluating. That is at picogram level. That is 10 to the power of minus 12. 10 to the power of minus 12 level, you can do this evaluation using this ELISA and RIA. Let us see the details. Let us go through the video.
For this experiment, you will need a microtiter plate, phosphate buffered saline, antibody and antigen samples, a color-changing substrate solution, a 37-degree incubator, an adjustable micropipette and tips, and transfer pipettes. Step 1. Label the microtiter plate and transfer pipettes as noted in the product literature. Step 2. Add 100 microliters of the antigen solution to all of the wells. Step 3. Incubate for 5 minutes at room temperature. At this time, the antigens will non-specifically adhere to the plastic through hydrophobic and electrostatic interactions. Step 4. Remove all the liquid from the wells using a transfer pipette. Step 5. Wash the wells by adding approximately 8 drops of PBS buffer to each well. Remove all the PBS from each of the wells, taking care to prevent the buffer from spilling over into adjacent wells. Traditionally following this step, the wells are blocked with a protein-containing buffer to prevent non-specific interactions between the antibody and the plastic wells. We have optimized this experiment to eliminate this step. Step 6. Add reagents as outlined in the product literature. Remember to use a clean micropipette tip for each reagent. Step 7. Incubate the plate for 15 minutes at 37 degrees Celsius. Step 8. Remove the liquid from the wells using the appropriately labeled transfer pipette. Step 9. Wash each well with fresh PBS. Remove the liquid using the transfer pipette designated for each sample. Step 10. Add 100 microliters of the secondary antibody to each of the wells. Step 11. Incubate for 15 minutes at 37 degrees Celsius. Step 12. While the samples are incubating, prepare the detection substrate as specified in the product literature. Step 13. Remove the secondary antibody solution from the wells using the transfer pipette designated for each sample. Wash each well once with fresh PBS buffer. Remove the liquid using the transfer pipette designated for each sample. Step 14. Add 100 microliters of the substrate solution to each well. Step 15. Incubate at 37 degrees Celsius for 5 minutes. Step 16. Examine your results. Differences between negative and positive samples will be obvious, with most positive samples turning brown in color. If color is not fully developed after 5 minutes, incubate at 37 degrees Celsius for a longer period of time.
So just now we have gone through a very nice video describing about the procedure of Elisa technique. Let us again review the same now. So the objectives of this particular presentation is to familiarize with the technique of Elisa, enzyme linked immunosorbent assay, to learn the technique of radioimmunoassay, for which the Nobel Prize was given to Rosalind, to understand the advantages and disadvantages of radioimmunoassay, to know the application of ELISA and RA applications. Okay, applications of ELISA and RIA. Expected outcomes. So the steps involved in ELISA, starting from the antigen blocking. Here the term like blocking is very much interested. Capture antibody, detecting antibody, blocking, capture antibody, detecting antibody, and substrate. Apart from that, there is another procedure involved here. Every step called washing. So you will get word of the washing here, but the final reading will be known. Okay, the steps involved in RIA using radioactively labeled antigen with tritium, C14, and again I-125 for the evaluation in the sample will be known. Okay, the applications of ELISA and RIA will be known. So enzyme linked immunosorbent assay, the term was first coined by Engel and Perlman, and there are different types: sandwich, indirect, competitive. Sandwich, indirect, competitive. Okay, so similar to RIA, except there is no radioactively labeled compound is used in ELISA. In ELISA, no radioactively labeled compound are used. Can be used to detect both antibody and antigen in ELISA. That's what in our COVID test, what we are doing in the rapid blood test, we are estimating the antibodies present in the patient serum. Very sensitive at picogram per ml. Relies on monoclonal antibodies, that is 10 to the power of minus 12. So ELISA work can be done only with the monoclonal antibody. Without monoclonal antibody, you cannot do. That is what this came after the hybridoma technology. So let us see now a simple technique called indirect ELISA. So here, this is a micro titer plate having 96 wells, wherein one plate enlarged well is shown here, wherein antigen coated wells. The wells are coated with antigen. Later we are coating, but we take the antigen in solution, pour the solution into the well, and all because it happens to be the plastic type, the protein gets stuck. Okay. One more thing here you see one antigen to the other antigen, there is a gap. That gap has to be blocked. That's what the blocking. Otherwise, immunoglobulins will get stuck. Okay. So next is the wash. That is unbound and uncoated or unbound antigens have to be eliminated by wash. Later we add the specific antigen, antibody. Antibody will get bound to the epitopes of the antigen. Okay. Later again what? That is unbound antibodies need to be removed. Okay. Later again we add another antibody with enzyme. Enzyme, that is here we use HRP, horse radish peroxidase, and alkaline phosphatase enzymes. Okay. So once that get bound, that's what we say indirect. It's not direct. Secondary antibody, that's what called the detecting antibody. The first one is the capture antibody, the second one is the detecting antibody. Okay, so that in the next one we will put a substrate called TMB. Okay, tetramethylbenzidine. So that with that substrate we get a color. That color we are reading here. That's what indirect ELISA. Next one is the direct ELISA. So sandwich ELISA. Okay, in the sandwich ELISA, what is happening is to begin with we put the antibody coated wells. And later we add this antigen. So antigen will get bound to the Fab region of the antibodies. Okay, here every time washing is required because unbound floating antibodies or antigens need to be washed up. Okay, so later we are putting the detecting antibody here. Detecting antibody with the enzyme. All through the ELISA, we use only alkaline phosphatase or horseradish peroxidase, horseradish peroxidase, HRP we used to say. Okay, peroxidase. And later we use TMB, tetramethyl So it provides the color. So here sandwich means the antigen is in between capture antibody and detecting antibody. Okay. So the next one is the competitive. It is a little bit complicated, we have to understand. So here we incubate antibody with antigen to be measured. So here add antigen antibody mixture to antigen coated well. Later we are adding, that is fixed concentration. Later we are adding this serum containing these antibodies and they will bound. So here there is a sort of competition is there between among the capturing antibodies. So as a result, how much of the serum antibodies bound here, that is going to be estimated through the detecting antibody, again to the same TMB. Okay, so this procedure we get to know sooner. So now the competitive ELISA C now, that is the last one we are showing.
Hello friends, today we are going to discuss about competitive ELISA. Competitive ELISA is used to determine the concentration of either antigen or antibodies present in a particular sample. Let us discuss how this particular technique is used to determine the concentration of antibody. Suppose we have to determine the concentration of anti-A antibodies from a serum sample, that is, the antibodies which specifically binds to the A antigen. For this, we will require A antigen in this case, means you must have the antigens specific to the antibodies whose concentration is to be determined. For example, if you want to determine the concentration of anti-HIV antibodies from the sample, you must have HIV antigen with you. Second and the most important thing that you must have is the enzyme linked anti-A antibody. This antibody, it also binds to the A antigen like the antibodies which are present in the sample. But these antibodies, they are coupled to the enzyme. The enzyme can be horseradish peroxidase, beta-galactosidase or alkaline phosphatase. All these enzymes have chromogenic substrates. For example, TMB, that is tetramethylbenzidine, which is the substrate of enzyme horseradish peroxidase, gives blue color when converted into the product, and its intensity can be determined by spectrophotometric method. In the first step, a microtiter well is coated with A antigen like this. The coating is mediated with the help of coating buffer. After this, the sample containing anti-A antibodies whose concentration is to be determined and a fixed amount of enzyme linked anti-A antibodies are added to the well. These two types of antibodies will compete with each other to bind the antigen present in the well. Now you might think, which type of antibody is going to win this competition? Well, the antibody with the greater concentration wins the competition. Now we don't know which kind of antibody's concentration is more. Let us assume both the situations. If the concentration of antibodies from the sample is more than enzyme linked antibodies, as in this case, these antibodies will occupy most of the antigens of the well. On the other hand, very few enzyme linked antibodies will bind to the antigens. But if the condition is reversed, as in this case, most of the antigens will be occupied by the enzyme linked antibodies. After this, the well is washed to remove unbound antibodies. This step is followed by addition of chromogenic substrate and incubation for a fixed period of time. After incubation, the reaction is stopped by adding strong acids. Now during this incubation, the enzyme connected to the enzyme linked antibody will convert this substrate into the color product. Now if the number of enzyme linked antibodies are less in the well, as in this case, less product will form, and hence the color intensity and its absorbance value will be less. And if the number of enzyme linked antibodies are more in the well, as in the second case, more product will form and therefore absorbance value will also be more. So in short, if the absorbance of the product is less, concentration of antibodies in the sample is more, and if the absorbance is more, the concentration of the antibodies in the sample is less. The actual concentration of antibodies present in the sample can be determined by extrapolating the value of absorbance on the standard graph like this. So in this way, the competitive ELISA is used to determine the concentration of antibodies. Exactly reverse method is used to determine the concentration of antigens.
Then now let us explain the sandwich ELISA. One ELISA, as we have seen earlier diagram. Sandwich ELISA requires two antibodies. One is the capture antibody, the other one is the recognizing antibody. Okay, so capture antibody, the other one is the detecting antibody. Okay, so the detecting antibody is biotin related. Biotin is one of the big complex vitamin. So enzyme usually called HRP, half radical peroxidase or alkaline phosphatase. Okay, here the substrate, as I mentioned to you earlier, it is a common thing world over, keep using TMB, that is tetramethylbenzidine. So this is what here that we also explained earlier to you, the same thing. Sandwich means the antigen that of our choice is coming between the capture antibody and the detecting antibody. Okay. So addition of the detection antibody. So here the detection antibody, here is only the technique, the different companies are providing the different ELISA kits wherein they streamline and refine the technique, because here avidin is a hen oviduct protein. Avidin has got high affinity towards biotin. Okay, biotin is nothing but B vitamin. So now they are adding the enzyme coupled with HRP enzyme coupled with avidin, so that the HRP is almost stable there. So for which purpose they use the avidin and biotin here. So now additional substrate, as we have seen the serial dilution. In this way we maintain the what is this called the substrate concentrations, and again the substrate here is the TMB, tetramethylbenzidine, that also we take in the diluted concentration, because everything is in 200 microliters. 200 microliters we have to do. We mix in 1:1 volume, and the substrate has to be added after the detecting antibody is added, because detecting antibody is having HRP. Okay, and here ultimately we are, after adding the substrate, color develops. Okay, if you keep waiting means color intensity becomes more. So as a result, we have to terminate the reaction by adding 0.5 molar sulfuric acid. So as a result, the color changes from blue to yellow. So we have to maintain the timings here, as we are seeing here the side strip also. We have to read the plate at 450 lambda. Okay, that is what the ELISA. So now let us see the principle of radioimmunoassay. Radioimmunoassay technique has come earlier than the ELISA technique. Okay, so for which only the Nobel Prize was given. So in this case, it uses immune reaction to estimate a ligand. Immune reaction means an antigen and antibody reaction. Now let us see the equation that is shown. Antigen plus another antigen which is labeled plus antibody. Okay, so we have taken normal antigen labeled and antibody. That will give antigen antibody complex. And again it also gives antigen antibody radio labeled complex. And antigen separate, antibody separate, excess they will be released out. Okay, so in this case, two things we are getting: antigen antibody complex, antigen antibody radio labeled complex. Okay, now we are going to estimate in scintillating counter this labeled compound only. Okay, here again inverse relationship come. I will let you know, like competitive ELISA. Unbound antigen antibody is washed up. Radioactivity of bound residue alone will be measured. Ligand concentration is inversely related to, that's what, inversely related to the radioactivity. Okay, so that's what we have to understand here. So this is again a video to explain to you about this radio RNA, radio.
Welcome back friends, this is Sajid Sheikh, and in this video session we will learn one more immunological technique which is known as radioimmunoassay. So basically this technique is used to determine the concentration of antigen present in the sample. This antigen can be anything. It can be hormone, it can be serum protein, it can be drug molecule, or it can be vitamin. The technique was originally developed by Burson and Yalow in 1960, and for this work they also received Nobel Prize in 1977, but unfortunately after the death of Burson. This technique is so sensitive that it can detect 0.001 microgram of antigen per ml of sample. So let us see how this technique is actually performed. Let us assume we have a serum sample and we want to find out the concentration of A antigen present in that particular sample. If we wish to do this, we must have three things with us. First is anti-A monoclonal antibodies against the antigen. That is, this antibody will bind to A antigen present in the sample. These antibodies are generally prepared by hybridoma technology. If you wish to learn more about this technique, click on the link given in the description of this video. Second thing is radio-labeled A antigen, means some part of this antigen is made up of radioisotopes so that they can emit radiations like gamma or beta. Generally, heavy isotopes of hydrogen, that is tritium, or iodine 125 is used for this. And the last thing, same A antigen in unlabeled form, that is the original form. So these three things, that is anti-A antibody, radio-labeled A antigen, and unlabeled A antigens are very important if we want to find out the concentration of A antigen present in the sample. If we don't have these things, we cannot find the concentration. In the first step, a micro titer plate is taken and then it is coated with anti-A monoclonal antibodies. After this, radio-labeled antigens are added to the well, but in the excess quantity. Now what will happen if the concentration is kept high? Since there are large number of antigens, all the antigen binding sites of antibodies will be saturated by the antigens. No antibody will be left free. As you can see, some radio-labeled antigens are left unbound. They are not bound to the antibodies. So in the next step, these unbound antigens are removed with the help of washing. See, what is the situation now? There is a well coated with the antibodies and all the antibodies are bound to the radio-labeled antigens. And therefore, let us assume the radioactivity of antibodies or present on the antibodies is 100%. Since all the antibodies have radio-labeled antigen, this is very important. Radioactivity in the antibodies or well is 100%. After this, a very small but known amount of unlabeled antigen is added to the well, say 1 nanogram. So we have added 1 nanogram of unlabeled antigen to the well. What is the effect of this? This addition will create the competition between radio-labeled and unlabeled antigen for binding antibodies, and this competition is proportional to the concentration of unlabeled antigen added to the well. Since we have added only 1 nanogram of antigen, competition will be less. and few radio-labeled antigens will be removed from the antibodies. And of course, their place will be taken by unlabeled antigens. After this, the well is again washed to remove unbound antigen, whether it is labeled or unlabeled, but unbound antigens. Now, what is the situation this time? Number of radio-labeled antigens bound to the antibodies are decreased due to the addition of unlabeled antigens, and hence the radioactivity present on the antibodies is not 100%. So we will write here, when unlabeled antigens were not added to the well, that is 0 nanogram, radioactivity was 100%. Okay. When 1 nanogram of unlabeled antigens were added, it decreased due to the competition, and let us assume it decreased by 90%. Actually, the 10% decrease, it became 90%. Now tell me, what will happen if we repeated all the process again, but by increasing the concentration of unlabeled antigen? First, let me write the things here. So first we added 0 nanogram of unlabeled antigen and radioactivity was 100%. Then we added 1 nanogram of antigen and radioactivity became 90%. Now tell, what will happen if we further increase the concentration of unlabeled antigen, say 2 nanogram? Yes, the radioactivity will further decrease, and it will be proportional to the concentration of unlabeled antigens added to the well. So if it became 90% for 1 nanogram, it may decrease to 80%, right? What about 3 nanogram? Yes, it will decrease to 70%. So every time we have to keep on increasing the concentration of unlabeled antigen and monitor the decrease in the radioactivity. So let me write the whole data here. So for 4, 60, for 5, 50, 40, 30. This is just an example. The actual values will be different. Now tell me what you see. Is there any relationship between unlabeled antigens added to the well and radioactivity? Yes, there is. And we can draw a linear graph using this data, correct? So let us draw it like this. Remember, we have not used sample yet. Don't forget, we have to determine concentration of A antigen present in the sample. Now the time of sample. We have to do all the steps again. We have to again take microtiter plate, then coat it with the monoclonal antibodies, then again add the excess amount of radio-labeled antigen, but we will not add unlabeled antigen this time. Instead, we have to add this sample. See, there are A antigens present in the sample, but we don't know the concentration. But according to the concentration, they will compete with the radio-labeled antigens and will remove them from the antibody. Now we have to just check the radioactivity. Say radioactivity on the antibodies is now 40%. Here we know that if we added the sample, it will decrease the radioactivity to 40%, and this value will tell us the concentration. We have to extrapolate this value on standard graph like this and see, it will tell us the concentration. It is 6 nanogram. So our sample contains 6 nanogram of A antigen. So in this way, radioimmunoassay is used to determine the concentration of unknown antigen.
Okay, so what are the advantages and disadvantages of radioimmunoassay? So it is highly specific. Usually those were the days the mothers who are unable to conceive the babies. For them, there is estrogen concentration in the blood serum is the hormone estrogen. So for the estimation of that hormone, we were not having any device. We used to go to the RIA to either to Madras or to Bombay to give our samples to estimate through this scintillation counters, GM counters, Grieger-Muller counters, scintillation counter. So those were the technique. Now that is improvised and simplified in ELISA so that in nook and corners we can estimate the estrogen levels now. Highly specific, immune reactions are specific, highly sensitive, immune reactions are sensitive. Disadvantages are radiation hazards, uses radio-labeled reagents, as I have shown you, tritium you are using, C14 compounds we are using, and I-125, iodine 125 you are using. They are all radio-labeled compounds. Okay, requires specially trained persons because one has to be trained in BRC, Baba Atomic Research Center, in nuclear chemistry. Okay, lab requires special license to handle radioactive. So we cannot, every lab cannot do because disposal of this radioactively compounds is again we can't leave into the waters, drainage. It has to be kept separately. Requires special arrangement for requisition, storage of radioactive materials, radioactive waste disposal. So these are all various hindrances to be evaluated here. Applications of ELISA and RIA. Detection of viruses, pathogens such as hepatitis, HIV, coronavirus, you can do through ELISA. RIA. Nowadays, people are all adopting ELISA. Okay, so detection of platelet antibodies in serum to identify patients suffering from disorders such as idiopathic thrombocytopenic purpura and systemic lupus erythematosus. These tests use the enzyme alkaline phosphatase, which is labeled with anti-human IgG. There are several examples like this. Even cancer screening and pregnancy test is done through the ELISA. Okay, nowadays there is no requirement to go to the microvalve plate. It has now come. The strips, ELISA strips also have come. Okay, detect and quantify molecules such as hormones, peptides, antibodies, antigens and proteins in serum for the purpose of diagnosis. All that is being done using the ELISA and RIA. Summary. So the protocol describing the steps involved in ELISA is elucidated. Different types of ELISA tests for the detection of antigen at a concentration of picogram per ml is shown, that is 10 to the power of minus 12. The technique of RIA and its advantages and disadvantages are detailed. Particularly RIA means it is radioactivity involved, so that we can't dispose just like that, so that there is certain sort of restrictions using radioactive labeled compounds. The applications of ELISA and RIA are enlisted. Okay, study questions with this have this as home assignment. Elaborate the procedure to perform sandwich ELISA. So if you elaborate this, you will be knowing the total ELISA technique, where the blocking has to be take place, where the washing has to be take place, where the bounding of these compounds within the ELISA plate takes place. All these things will be known to you. Where the capture antibody is added, where this detecting antibody is added. All these things will be known here. Why blocking of ELISA plates are done? What significance does it have in ELISA? Okay, at what concentration does the antigen will be determined in ELISA? Okay, elaborate the procedure of RIA. What are the disadvantages and advantages of RIA? Enlist the applications of ELISA and RIA. Okay, so with this, we sincerely acknowledge online resources and public domains that have been used here for developing this content for our teaching material. Thank you one and all.